recording. I will also start recording now.
Thank you, Chamira. Well, it's great pleasure to give this talk to our Sri Lanka.
Hello, good morning, everyone. If you are in Sri Lanka, and good afternoon or good evening, based on your locations, wherever you are in the world or the earth. So this is the sixth webinar of our monthly webinar series organized by the IEEE Student Signal Processing Society Student Branch Chapter of the University of Moratuwa. Today, our guest speaker is Professor Aleksander Lgnjatovic. So he's an associate professor at the University of New South Wales, Sydney, Australia. Professor Alex received a PhD degree in mathematical logic from the University of California, Berkeley. He is an associate professor in the School of Computer Science and Engineering at the University of New South Wales, as I mentioned earlier. His current research interests include approximation theory, sampling theory, and applied harmonic analysis, algorithm design, and applications of mathematical logic to computational complexity theory. He has authored numerous conference and journal papers. Also, he has a few US patents. So he's the inventor of the chromatic derivatives. So we are listening to him today. I would like to invite Professor Alex for his talk.
Thank you very much for your kind words. So let's see what this talk is about. But before we start, in case you get interested in this topic, the details on the theory can be found in a few papers of mine that I have published over the years, but the most complete account is probably this manuscript that is kind of always in progress as I keep working in this field, but it probably contains the most detailed description of the state of the art of this theory. When it comes to applications, they were done mostly with my colleague Chebyshev from University of Queensland. And here you have a list of some representative papers. And I sent to Chamira these slides. So if you get interested and you want to look at these references, please ask Chamira to send you a copy of the slides. So to explain this in some sense, a little bit esoteric theory, we should start with the Shannon expansion and to motivate why we introduce these new concepts. So even though the theory is applicable to non-band limited signals and signals with infinite energy, for our purpose, it will suffice if we restrict ourselves to band limited signals of finite energy. Finite energy simply means that they are square integrable, and we will choose the time measuring unit so that the frequencies are all normalized between minus pi and pi. So, of course, this is the holy grail of signal processing, probably the most important formula in signal processing, which is usually called Shannon's expansion, that tells us if we normalize frequencies to the bandwidth of minus pi to pi, then the value of a band limited signal is completely determined by its values on integer samples. Now, this formula is global in nature because this summation uses samples from minus infinity to infinity. And in fact, its truncations poorly represent signal. So for example, if you truncate this expansion, so you use 2m plus 1 samples only. And you want to find the value of the signal at 1/2. So between the sample at 0 and sample at 1, when you substitute t by 1/2, you get this expression. And what we can see immediately is that this multiplier, the factor that multiplies the sample, is behaving approximately as 1/πn. So this means that these multipliers decrease very, very slowly. So if you want to make sure that the first sample that you drop will have impact less than 1 bit, when with say only 12-bit accuracy, we need m bigger than 1300. So truly gigantic number of samples are needed to use Shannon formula to precisely interpolate a signal. And of course, this fact is well known to engineers. Audio engineers found out early on that if you use Shannon formula to oversample the signal, you can get very nasty transients. So there are, of course, then much better, much gentler way to do oversampling. So the bottom line is that this formula really doesn't allow us to capture the local behavior of the signal. Now, on the other extreme is the Taylor expansion. So Taylor expansion is local in nature because instead of requiring samples from -infinity to infinity, it requires the values of the derivatives of the signal at a single point in time. And of course, theoretically, from a mathematical perspective, these values are completely determined by an arbitrarily small neighborhood around 0. If you could analytically differentiate the signal, if I gave you a small slice of the signal, you can find all these derivatives. And in fact, if you truncate the Taylor formula, you get excellent local approximations, because a Taylor formula approximates not only the signal, but its derivatives approximate the derivatives of the signal. If you take a Taylor formula of degree m and you differentiate it k times, you can quickly see that what you get is the Taylor formula of the kth derivative of order m minus k. So the derivatives of the Taylor formula approximate accurately the derivatives of the signal in a neighborhood, of course, that decreases in size as k increases, because the degree of the expansion of the derivative gets progressively lower and lower. Now, however, Taylor formula has seen very little use in signal processing, and this is for a very good reason. So let us now briefly compare the Shannon formula with the Taylor formula. First of all, Taylor formula involves derivatives of high order. And of course, it is well known to numerical analysts that evaluation of derivatives of high orders is extremely noisy process, extremely noise sensitive, and you are cautioned always to replace, to avoid differentiation whenever possible. But it has further disadvantages, the Taylor formula. So if you compare it with the Shannon formula, if you truncate the Shannon formula, this truncation is still a band-limited signal because it's a linear combination of shifted sinks. And of course, such a linear combination of band-limited signals is itself a band-limited signal. And if you truncate the Taylor formula multipliers are monomials, right? T to the n over n factorial, which of course are not band limited signals. So you are approximating, if you do Taylor approximation of a band limited signal using Taylor formula, you are using extraneous objects, the monomials, which are not band limited signals, to approximate a band limited signal, and clearly this must be suboptimal. And of course, also Shannon formula converges to the signal in the sense of L2 norm, which means that if A is a filter, you can pass through infinite summation and apply it, and also through the time shifting, and apply it just to the sink. So if you know what the operator is doing to the sink, you can tell what he's doing to an arbitrary band limited signal. And of course, nothing of this is true of the Taylor formula. So now what inspired all this research is, can you fix all of the problems that Taylor formula suffers? So can you find a formula which has all the good properties here listed of the Shannon formula, but still maintains the nice local approximation that Taylor formula provides? Now, you might wonder, why do we want local signal approximation? Well, we will see later that for some tasks like finding zero crossing of the signal, local approximation is all that matters, right? If you want to precisely determine the time when the signal will cross the x-axis. And of course, hopefully, local approximations are also important for image processing, because local errors in images can be highly disturbing, right? So this is our aim. Can you replace the standard derivatives with something that is numerically robust? And can you replace the monomials with functions that are themselves band limited functions, so that this becomes kind of internal approximation that would share all these wonderful properties of the Shannon expansion? So in order to kind of explain why we are doing what we are doing, let us first investigate what are the problems of numerical differentiation of band limited signals. So if F belongs to the space of band limited signals of finite energy, then we can represent it using the Fourier transform. And if you differentiate such a signal, you can enter with differentiation under the integral sign. The Fourier transform does not depend on t, so you're differentiating e to the j omega t, and the derivative is of course j omega. So if you do it n times, you will get a multiplier j to the n times omega to the n. Now, omega ranges from -pi to pi, so having omega to the n is inconvenient for comparison purpose. So what we are going to do, we are going to normalize this derivative by dividing nth derivative with pi to the n. So now the transfer function of this normalized differentiation is omega over pi to the n. And we can now look what these transfer functions do to the Fourier transform. And lo and behold, that's easiest to see using a picture. What you see here are the plots of omega over pi to the power n for n between 15 and 18. And this immediately tells you why it absolutely makes no sense to look for the derivatives of high order of a band limited signal, excuse me. First of all, derivatives of high order kill the spectrum. So this guy is multiplying the Fourier transform, but it's essentially zero over most of the frequency domain, and it leaves out only the edges, but the edges, because of right, the band, the guard band that we always apply, the edges only contain the noise. And moreover, you can see that the derivatives of different orders, say 15 and 17, that are of the same parity, both even or both odd, are indistinguishable from each other, because these factors barely differ between between orders 15 and say 17. So this clearly shows that it makes no sense to find high order derivatives of band limited signals. So, but you see, we seldom need the derivatives per se. Usually, just like if you think about control theory, we need differential operators, right? That correspond, for example, to the transfer functions of with rational, right, transfer functions of our systems. So the question is, maybe we can still represent accurately these differential operators, except that the basis, the standard basis of the vector space of linear differential operators, namely f, f prime, f double prime, f triple prime, is just no good. So what is the best basis in general? Of course, this is orthogonal basis. So can we find a notion of orthogonality and families of orthogonal differential operators? Well, just to remind you, the usual scalar product of integrable functions, possibly complex valued, is defined by this formula, which we can mildly generalize by introducing a weight, which is a non-negative function that integrates to 1. You can think of W as a probability distribution. And then you can form a scalar product in which this product of the functions is multiplied by the weight, right? So essentially you are giving different weights for different frequencies, because we will be applying this in the frequency domain. And just to remind you, f is orthogonal to g, just in case the scalar product is 0. So how can we then find an orthogonal basis for the space of linear differential operators? As an example that turns out to be the most important one, we will start with normalized and rescaled Legendre polynomials. So remember, Legendre polynomials are usually orthogonal between -1 and 1, but we scale the variable dividing it by pi so that they become orthogonal between -pi and pi. And we normalize them so that the scalar product of two normalized Legendre polynomials are 1 if m is equal to n. Then what we do is we obtain differential operators by replacing omega with -j times the derivative with respect to t. And here the powers, so omega to the k will be replaced by kth derivative with respect to t. So to give you an example, the first polynomial is just 1. So there, its degree is 0. So here we will have 0th order differential operators. So it will be just f of t. Then p1 of omega is √3 omega over pi. This becomes √3 f prime of t divided by pi. And as you can see here, we replace omega squared with the second derivative. And these j's and minus j's, their whole purpose is to flip this sign from negative to positive. And so what I call these differential operators chromatic derivatives associated with the Legendre polynomials. And they're just linear differential operators. So they are linear combinations of the standard derivatives. So why would one introduce such strange operators? Well, the definition of k to the n of such a differential operator is chosen precisely with the aim that when you apply it to the Fourier kernel, you get j to the n times the orthogonal polynomial that multiplies the Fourier kernel. So this means if you have a function f that is band limited and you apply such differential operators to such a signal, instead of omega over pi to the n that we had here, you will now have as a multiplier as the transfer function j to the n times the orthogonal polynomial in omega. So why do we introduce such operators? Well, the picture is worth 1,000 words, what they say. So on top you have the transfer function of the standard differential operator, normalized only, right? So the transfer function will be omega over pi to the n, and we saw that it ruins the spectral content of the signal, while the transfer function of these chromatic derivatives, when you plot them, you get a family of interleaved, increasingly refined comb-like filters, right? And notice these filters don't kill any part of the spectrum, right? And as you increase the order, they just encode spectral features in a more and more refined way. So I call them chromatic derivatives because chroma is color, right? So they preserve, quote unquote, the color of the signal, namely the spectral content of the signal. And lo and behold, if you try to implement it here, I took an extreme case just to show you what you can do. This is the frequency response of a filter that approximates the chromatic derivative of order 127. So it is differential operator of order 127. And you can see that in 90% of the spectrum where your content of information of your signal is accurate with accuracy 2 times 10 to the minus 4. And in the edges of the spectrum, it doesn't blow up the noise at all because it remains essentially between -1 and 1. So it will not amplify the noise. And we have tested in practice such transversal filters, such FIR filters, and they live up to their mathematical promise stated here. You can find chromatic derivatives of orders of extremely large orders for as long as you have sufficient number of taps. In practice, we use only 65 or 128 or 29 tap chromatic derivative filters. So these guarantees that these operators will not suffer from the noise sensitivity that standard derivatives suffer. So you can evaluate them with huge precision, but that's not the end of the story. They turn out to have truly spectacular properties. So if you take any signal, band limited signal of finite energy, right? Something that looks like this. And then you evaluate derivatives of all orders at a certain point t, and then you do the same at another point u. So t and u are arbitrary points, and you find some of the squares of derivatives here and some of the squares of derivatives here, you get exactly the same value. So sum of the squares of chromatic derivatives is independent of time instant, and it turns out that it is precisely equal to the L2 norm of the signal. So you have a totally local, right? Because these are just derivatives, differential operators, totally local representation of a totally global quantity, namely the L2 norm of the signal. And the same applies to scalar products. The standard scalar product is also representable as infinite sum of products of chromatic derivatives of the two signals, and the same is true of convolution. So this allows you, this provides you local equivalence of the usual globally defined norm, scalar product, and convolution. And the aim is, of course, where we are going with all of this, is to do some highly localized signal processing. Okay, but we still haven't done the main task, which is fixing the Taylor expansion, right? You remember we had a problem with the fact that these derivatives are noise sensitive and that the monomials are not band limited signals of finite energy. Well, what one can show is that if you have any analytic function, f of t, then it has the following expansion. This expansion, notice, is obtained by replacing the standard derivative at 0 with the values of these chromatic derivatives at 0, and the monomial t to the n over n factorial we replace with -1 to the n times chromatic derivative of the sinc function. But this is a band limited signal itself. And it happens to be precisely this value here. It happens to be just square root of 2n plus 1 times the spherical Bessel function of the first kind of order n. So this is a band limited signal, the Bessel functions. And so if you truncate this formula, you will get a band limited signal instead of polynomials that you get if you truncate the Taylor formula. So in this way, we both took care of the noise sensitivity of the derivatives and of the fact that truncation of the Taylor formula of a band limited signal was not a band limited signal itself. Now, if instead of just doing this for any analytic function, if you apply it to band limited signal of finite energy, then this series converges both uniformly and in L2. So in fact, you can now pass with a filter both through the sum, through the scalar multiplier, and every filter commutes with another filter, which is just a chromatic derivative. So you get that to apply a filter to f, all you have to do is apply it to the sinc, and then form this sum. And here is a plot. So red is a band limited signal of finite energy obtained using the Shannon formula with 1000 samples on the left and 1000 samples to the right. Green is the Taylor formula of order 15. So you can see, and that's the main reason why you cannot use it for interpolations, is because as soon as you leave the neighborhood of the point of expansion, it explodes, right? Because polynomials grow extremely fast. Blue, on the other hand, is the chromatic approximation of the same order. And you can see that it is accurate about twice as long interval as the Taylor formula, and instead of exploding, it just gently wavers and dies down when you move away from the point of expansion. So something that behaves in this way is clearly optimal for interpolation of the signals, because it will capture local behavior of the signal far better than the Shannon formula. Now you see, if you apply filters, right, you might wonder, well, you still use only Shannon type, you have Shannon type information, right? But this is not true. You see, Shannon formula is blind to the fact that 10% of both ends of the spectrum are just noise. Shannon formula treats the samples as critical samples and assumes whole bandwidth minus pi to pi. And these chromatic filters, they actually are tailored. They know that the signal is only in 90% of the bandwidth. So they are able to extricate extra information by knowing that the samples are not uncorrelated. They are not critically sampled, but they are sampled with slightly higher density than critical density. And this information that is buried in the autocorrelation of the samples that are taken at a slightly higher rate than the critical rate is then used to approximate the signal locally in a much more accurate way. So now, we dealt so far only with the Legendre polynomials and the associated chromatic derivatives, and they're good for representing, so to speak, generic band-limited signals, because the previous theorem, let me just quickly show you, this theorem, it says that the series converges to f of t both uniformly on the whole of R and in L2 precisely for band-limited signals of finite energy. So, however, the technique is highly adaptable, and you can actually tailor-made it if you know that the expected spectrum of your signal has certain frequency profile. Then you can actually custom make both the chromatic derivatives and the associated expansion functions so that you optimally capture precisely these signals and maximally reject the noise that doesn't share the same spectral features. You can even capture band-limited signals that are not of finite energy. And you can even capture signals which are not band-limited for as long as their spectrum decays sufficiently rapidly as frequency increases, which is in fact always the case for non-band-limited signals that infrequently do come in practice. So what one can do, I will now just very briefly tell you, the whole machinery can be relativized to a weight, right, that is positive, non-negative, and integrates to 1 and even doesn't have to be band limited. The only assumption to make the machinery work is that the moments, so what are the moments? Just like in statistics, it's just integrals of omega to the n times the probability distribution, right? They should not grow excessively fast, namely nth roots of the moments divided by n, the limit superior, essentially they have to be bounded. This ratio has to be bounded. As soon as this is satisfied, the whole machinery works perfectly well. And as I mentioned, this condition simply says it's equivalent to the following statement that this integral is finite. So this means that the weight has to go to 0 as omega increases faster than e to the alpha times absolute value of omega. So it has to have a slightly faster decaying rate than the exponential function. And this is in fact the case for important families like the Hermite polynomials and the similar. So then you can introduce polynomials that are orthogonal with respect to this weight and repeat the whole process. So now instead of finite energy, namely integral in the frequency domain of the modulus of the spectrum squared less than infinity, you have the same but with the weight. And the moment condition that I just shown you implies that these polynomials are complete in the space of all functions that are finite energy relative to this weight. You can then introduce orthogonal differential operators, where here instead of the Legendre polynomials, you have polynomials orthogonal with respect to the weight. And the whole machinery works perfectly fine. You can introduce energy in the time domain as sum of the squares of chromatic derivatives at 0, but this turns out to be independent of the point, so 0 can be replaced by any point t. And this expression has all the features that a norm should have. And this then again shows that chromatic derivatives are essentially the coefficients of representation of this weighted spectrum of the signal with respect to these polynomials, and that the norm in the frequency domain coincides with the norm in the time domain, just as it's the case with the standard Fourier transform. And you can then fix the Taylor formula accordingly. Instead of the spherical Bessel function, what you have to consider now is just the Fourier transform of the weight. And lo and behold, you get the same expansion, but this time this converges uniformly and in the sense of the norm for signals whose Fourier transform has finite W energy, right? Finite energy relativized to the weight W. So the bottom line, you don't have to worry about this mathematical mumbo jumbo. So the lesson that one can take out of all of this is that this theory is highly customizable, highly adaptive in fact, Chamit and myself have a denoising algorithm in which, as we denoise a signal, we also keep track of the noise, and then we custom make chromatic derivatives according to the noise profile. And it turns out that if the derivatives are orthogonal with respect to the weight that is power spectrum density of the noise, then chromatic derivatives of all orders are mutually uncorrelated. So then any statistical estimation becomes more accurate, of course. So just to give you an example, we saw Legendre polynomials that capture all pi band limited signals of finite energy. If you take Chebyshev polynomials, you capture all signals that now might have infinite energy because this integral has to be finite. Notice this is a semicircle, right? This square root of 1 minus omega over pi squared. So you get that the polynomial, the spectrum will be multiplied with semicircle, which means that the signal can have huge energy towards the edges of the band limit, right? Such as, for example, Bessel functions that in fact have vertical asymptote at the edges. So this family would be very good for capturing signals whose energy is mostly in the high frequencies. Hermite polynomials, on the other hand, provide you with an example of both differential operators and corresponding expansions that work for non-band limited signals. So for as long as the spectrum decays faster than e to the omega squared, right? If it has rapid, if it's essentially, if it decays faster than e to the minus omega squared, then the expansion still works. So the bottom line is the technique is extremely flexible. So what were we able to do with all this stuff, Chamit and myself, with some students and other colleagues? Well, just by using the fact that the functions, the basis functions, which are, for example, in case of Legendre polynomial spherical Bessel functions, have such good approximation property, you can use, for example, for non-uniformly sampled signals, you can retrieve uniform samples by simply putting least square fit, regularized fit, and the regularization factor mu. The procedure is almost insensitive to it if it's in the range between 10 to the minus 10 to 10 to the minus 14, it works equally well. So if you find x's so that the kind of hypothetical chromatic expansion, what is this sum? This is essentially chromatic expansion in which you don't know what chromatic derivatives are, so you put variables there. And these are the expansion functions, and you simply want such hypothetical expansion to get as close to the samples and sampling instance as possible over all samples. Once you find x hat that minimizes this expansion, and numerically this reduces to a single matrix vector multiplication when you explicitly solve when you set partial derivatives with respect to variables to 0, and you solve for them. Once you get the optimal values, then you simply use this formula to interpolate any signal. And results beat the state of the art for, I think, an order of magnitude, if not more. Then you can find zero crossings of signals with extremely high accuracy, again, precisely because this chromatic expansion approximation so faithfully captures the local signal behavior. We were able to find zero crossings with extremely high accuracy. And some of the algorithms for finding the direction of arrival use zero crossings, so this can be used there. Then you can recover signals using only timing information. So if up to multiplicative constant. So if I tell you, or rather if you tell me the zero crossings of your signal and positions of the peaks of the signal, we can reconstruct the signal modulo a scale factor, constant factor, with very high precision. And finally, what one can do is you can capture signals of very high frequency by sampling it in parallel at a fraction of a Nyquist rate, by sampling an analog filter bank built from all pass filters. This is work that Chamit did, I believe, in his thesis. So what you do is, of course, you cannot use ideal differentiator because it's so sensitive to noise. So you make it a practical differentiator by adding a capacitor in parallel with the feedback resistor. And then you sum it up, the output of this with 4 times the input signal. And if you cascade, in this case, we had 127 of these circuits, which can be, if I remember correctly from what Chabit told me, they can be actually realized with only 4 transistors. Then you can determine these constants, how to make a linear combination of the outputs of this cascade to approximate chromatic derivatives with extremely high precision, also of the order of magnitude 10 to the minus 4. And then what one can show, if you sample this filter bank at, say, if you have 16 such filters, if you sample the outputs of this filter bank at 1/8 of the Nyquist rate, you can almost perfectly reconstruct the signal with very high precision. And the samples between the sampling instants are reconstructed using only 2 consecutive samples of the filter bank. So you don't have to memorize, you only keep always only 2 samples left, and from there you can reconstruct the samples of the signal between the sampling instance of the filter bank. Now, what Chamit and myself would really love is if you get inspired being a practicing DSP engineers, what else we can do with this machinery, if for no other good reason, because it ate up my working life. I spent inordinate amount of time working out the mathematical details, which eventually get extremely involved, but they're kind of settled now. And wonderful thing would be if this can be applied to images or to whatever. You are the engineers, I'm not, I'm just a lonely mathematician. So thank you very much for your time. And I hope this was of some interest to you.
Thank you very much, Professor Alex, for your very interesting, basically introduction plus applications of the chromatic derivatives. And actually, there is a really useful webinar for our students and all the participants, I believe. And I would like to, I think there are some questions. Bhavan, could you please indicate those questions? Okay, in the chat. The question is, can we suppress the outside 50% of the spectrum instead of 10% using chromatic derivatives if we believe that all of that is noise?
Yeah, absolutely. In fact, you know, initially I didn't believe that you can find the derivatives with only 10% of extra bandwidth. And originally, and the first papers are written, I assumed that the signal is twice oversampled. So lo and behold, you can customate whatever is your bandwidth, whatever you know about the bandwidth, you can squeeze and half of the bandwidth would be perfect. Everything remains extremely robust. In fact, it's more robust that way than if you have only 10% oversampling.
Okay, so actually that is the only question from the yeah. So on the this slide of our question and answer platform, if any of the audience have other questions, so you can directly ask to Alex.
Yeah, please feel free to ask any questions you might have.
Okay, it seems that okay, so there is one question from the audience. Is all of the customization of the chromatic derivations done using the WX distribution? So basically, he's asking whether all the customization is done using that weighting function.
Yes, in fact, you can do it on the fly, believe it or not. You can say if you are tracking noise and if you are tracking, say, frequencies of a bunch of sine waves, and you keep subtracting them and tracking the power spectrum of the noise, you can on the fly use the power spectrum of the noise as the weight W to produce the polynomials and the operators on the fly that keep your operators orthogonal with respect to this W that is in fact the power spectrum density of the noise.
Okay, and so if the audience has any other questions, please free to share it with the chat or directly ask. Okay, it seems that those are the questions from the audience. So basically, I have several questions. So basically, in the first day, I have seen these papers from Chamit and Yuan. So I was really interested and on this one. And I see here this is a truly remarkable invention which has a lot of potential, especially for if we extend this to multidimensional signals, which I'm working on. And so basically, you mentioned that the several applications. One is the identification of zero crossing. So I have seen in previous work that the wavelets have been used for the identification of zero crossing. So how the wavelet approach and this is compare. And
well, yeah, when we did the zero crossings, we kind of looked in the reported literature, and in fact, I believe we were better than all of the state-of-the-art methods. So this is, in a sense, this is even more localized than the wavelets are.
Okay.
So it actually works better than wavelets. And what you said that you are interested in multi-dimensions, in fact, there is a version of this theory. There is a paper with my colleague Ahmed Zaid, in which usually when you do several dimensions, you take just tensor product of the dimensions, the basis, right? Yeah. But here you can have orthogonal polynomials in the spectrum that are whose supports are almost circular. For example, you can have hexagonal support or triangular support, so you are not bound to Cartesian product.
Oh, that's great. So basically, we could expand for this general sampling, not just the rectangular sampling.
Yep.
Yeah. And also the other thing. So the in the last slide, you mentioned that we could sample a signal with much less than the Nyquist rate. So basically, in the Nyquist sampling theorem, the basic assumption is the signal is band limited, and in the compressive sensing, so the sparse signal, so basically the assumption is the signal is sparse. So with this case, sub-Nyquist sampling, is there any assumption or properties?
Yes, you know, it's so you are sampling an analog filter bank at a fraction of the Nyquist rate, but you are sampling several of these filters, right?
Okay.
So you are, say, sampling every 8 Nyquist rate instant 16 filters. So you are essentially oversampling it. It's really not sub-Nyquist. It's time-wise, it's sub-Nyquist, but in terms of information, it's actually oversampling.
Oversampled. Okay, right. Yeah. That's true.
Yeah, this is Shannon. If I can also add a bit to that, I think in that it's kind of a parallel scheme to time interleaved sampling, but in the time interleaved sampling, you have a field, like you have parallel channels being sampled, but they are not sampled synchronously, right? You have a polyphase clock, and you run into synchronization issues, jitter, and all that. But in contrast to this approach, if it developed, it's actually synchronously sampling the analog chromatic derivative filter bank. So you take samples, so it's just a single clock.
And also, so what I feel is that basically, other than the applications you have considered, I have seen that this zero crossing is used in many industrial applications, even in this identifying faults in electrical motors and all of. What are the other interesting applications we could use this? Because even for for example, in this communication or these kind of things also could be incorporated, because one of the thing is that the massive MIMO or that kind of thing is they are, if they have large number of antennas, these high A to D converters with a large number of bits consume a lot of power. So they always try to go for the lower sampling rates, so the different quantization levels, low quantization levels. So could this be used for the applications you have not considered, and so any other potential applications?
I would hope so, and if you have good ideas, both Chamit and myself would love to hear them. I'm not an engineer, so in fact, when it comes to applications, Chamit was in the driver's seat, what to do. So I am hoping that there are applications that we haven't exploited yet So I would love to hear from everyone in the audience if you have any ideas where such highly localized signal representation could be used. I hope that the answer is yes, but I couldn't know really.
Yeah. Yeah, one thing came into my mind because I have seen a paper actually written by Emmanuel Candace. So he's from the, I think the Stanford, oh yeah, he's in California somehow actually. So they are trying to use the super resolution considering, and the one thing just came to my mind is if we consider the DFT, discrete Fourier transform, and in those cases, basically, we have the discrete samples of the spectrum. Probably we will miss, if we have harmonics, this exact frequency would be in between two samples.
Mm-hmm.
So could we exploit this into that kind of applications?
I think that should be possible, in fact, because these chromatic derivatives are coefficients of the expansion in orthogonal polynomials, so they should be able to capture. I was thinking myself about this super resolution business by putting again a hypothetical chromatic expansion and then imposing constraints that when averaged over, when the resolution is reduced to agree with the images that you have. So to find the best fit local signal that would be downsampled to look as images that you have. Yeah. I think this should be quite possible and even quite straightforward, but I have never done with images. I don't think Jamit also has done much with image processing, so we didn't try that, but I think that would be a prime suspect to try.
Yeah, definitely. I'm also really interested, and that one, and I really feel the significant potential of your invention.
I can only hope that I'm not ruining your career right now. It definitely ruined mine.
Okay, and so I think there are no more questions. So we may conclude the session. So before the conclusions, the secretary of the Signal Processing Society